An 8.35-kilometer launch rail, terminating at a 45-degree angle, is loaded with a vehicle mounted on a lightweight aerodynamic sled. The sled mates with two charged rails, delivering high-current DC power. Like a railgun, the current induces a Lorentz force on the sled of 2.23 meganewtons, accelerating it over 12 seconds and subjecting it to a maximum of 11.8 Gs. Damping systems in the crew capsule reduce felt forces on board to about 8.9 Gs. When the sled leaves the end of the rail, it's traveling at 1400 meters per second. Less than a second after exiting the launch rail, solid rocket boosters attached to the sled fire simultaneously. These are comparable to the Castor series motors manufactured by Northrop Grumman, each providing 350 meters per second delta V. These SRBMs fire for about 180 seconds and boost the vehicle up to just over 2100 meters per second, at about 1.5 Gs maximum. As the rockets burn out, the SRBMs separate from the vehicle and fall back to Earth. The vehicle is now well within the hypersonic velocity envelope, which begins at 1700 meters per second. The vehicle's scramjet is fed by compressed atmosphere from the vehicle's shock front, and as it ascends, the scoop is gradually opened using its variable geometry flap to increase airflow to the engine. The vehicle's initial 45-degree angle of attack drops to about 1.5 degrees, allowing the vehicle to gain more horizontal velocity before leaving the atmosphere. Liquid oxygen is provided by an air liquefaction system similar to that designed for the BAE Systems HOTOL concept, which converts high-pressure atmospheric gas directly into liquid oxygen for use as a rocket oxidizer. This allows the vehicle to take off with empty liquid oxygen tanks, which are filled during ascent. Because the scramjet is simultaneously burning liquid hydrogen fuel, mass of the vehicle only begins to increase once it has reached a suborbital trajectory, greatly increasing efficiency. The air intake features variable geometry to permit greater airflow at lower speeds, and splits incoming air into two ducts. Some feeds the scramjet, and the rest enters the oxygen liquefaction system. The scramjet accelerates the vehicle until the atmosphere is too thin to continue operation, boosting the vehicle to about 45 kilometers altitude, resulting in a final horizontal speed of Mach 22.9, or about 7.8 kilometers per second, and a vertical speed of about 1 kilometer per second. At this point, the atmosphere is too rarefied for continued scramjet operation, and a cluster of liquid hydrogen and oxygen burning rocket engines take over the ascent. During the ascent period, an array of ground-based microwave emitters are focused on the ablative shield on the bottom of the vehicle. These are positioned in a line below the predicted flight trajectory, and their beams reach 45 kilometers into the atmosphere. The arrays are spaced at least 500 meters apart, and up to 5 arrays focus on the vehicle at a time, creating a phased array effect over a large area, and a synthetic aperture effect, focusing on the 15-meter square ablator with relative ease. Each array has 2,000 elements, each producing about 25 kilowatts of microwave energy from magnetrons operating at 94 gigahertz. This frequency passes through the atmosphere, making weather a non-issue at the cost of slightly less energy delivery compared to lower frequencies. The beamed energy arrays only operate for about 100 seconds per launch. The ablative shield, made of graphene composite with an exhaust velocity of around 3,500 meters per second, reaches surface temperatures up to 4,000 Kelvin. The additional velocity imparted by this system decreases the amount of energy the vehicle must dedicate to ascent, allowing it to gain acceleration horizontally, thus reducing the amount of fuel needed to later circularize its orbit. The ablation happens quickly, with the shield losing around 4.5 kilograms per second. In a typical flight, the ablator reduces in overall mass by more than half, but due to the vehicle's wing characteristics, the remaining ablator is more than enough for atmospheric re-entry. 2 to 4 high ISP engines, rated at about 450 seconds in a vacuum, provide more than enough thrust to circularize the orbit and make interplanetary maneuvers. The spaceplane now has a few different options available, depending on its destination and what kind of space support architecture is available. We'll look at a few options, but first let's break down the vehicle's mass. We'll approximate the mass of our design's individual components by scaling down budgets from existing SSTO designs, notably Space Shuttle, Skylon, and HOTOL, and adapting those figures to meet our needs. Fuselage, wings, landing skids, plus structural supports equal about 2,320 kilograms. Vehicles like Skylon, developed in the 1980s, dedicated between 30 and 40% of dry mass to structure. Our vehicle uses 20 to 30%, reflecting material advances. Propellant tanks represent about 475 kilos. Liquid hydrogen is a relatively low-density fuel, so the tanks are large and insulated. And each 100 kilograms of hydrogen requires about 1 to 3 kilos of tank, assuming construction with aluminum-lithium alloys and carbon fiber. Liquid oxygen requires smaller tanks, and these will be spherical, not cylindrical, will stay on the modest end of estimation and work in the overhead later. If we convert the payload to fuel storage, an additional 150 kilos will be needed to account for tankage. The scramjet generates around 5.4 kilometers per second delta-v to ascend and approach orbital velocity. The scramjet mass is scaled down from Skylon's Sabre engines, which represented about 10 to 15 tons for a 325,000 kilogram vehicle, or about 4%. For a 20,000 kilogram vehicle, a 700 kilo scramjet, including variable geometry mechanisms, should suffice. About 4 km per second delta-v at 450 seconds ISP is provided by the engines. This figure is based on scaled-down SSME engines on the Space Shuttle, which were about 3,200 kilos each at 470 seconds ISP. Again, the total mass for our design is about 700 kilos, equal to the scramjet. During ascent, the air liquefaction system scavenges around 6,800 kilos of liquid oxygen from the atmosphere. Scaling down from HOTOL and Skylon, this system should represent around 1,000 kilos, including cryogenic engine plumbing. The propulsion systems combined mass in at about 2,400 kilograms. To supply both the scramjet and rockets, about 8,000 kilos of liquid hydrogen will be needed. Fuel will be burned at around a 5-to-1 ratio of oxidizer to fuel, but the total liquid oxygen capacity will be lower than expected, since around 6,800 kilos of liquid oxygen will be acquired by the air liquefaction system in flight. The ablator doubles as a heat shield, but is considerably lighter by volume than the ceramic tiles found on vehicles like the Space Shuttle. Total mass is about 590 kilos, providing 110 meters per second delta-v during ascent. Total propellant at launch, including the ablator, totals 14,900 kilograms, just under 75% of the vehicle's gross mass. 4 crew members wearing G-suits will total about 380 kilograms. The capsule mass itself is calculated by scaling down the Dragon capsule, which masses at about 600 kilos for a crew of 7. For 4 crew, the capsule, seats, dampeners, and instrumentation will be about 350 kilograms. Breathable oxygen, scrubbers, and temperature control for a nominal mission will mass about 125 kilograms. In total, the capsule, life support, and crew will mass at about 775 kilos. The navigation computers, guidance systems, communication antennas, flight control systems, and other critical components represent about 1.5% of the dry vehicle mass, or about 350 kilos. Although the ablator provides protection from re-entry heat, the rest of the spacecraft needs to be protected from thermal shock during hypersonic flight. Additional protection will add around 600 kilos overall. Other residual systems, such as wiring, flight control actuators, and overhead margins, add up to around 2% of the vehicle's total gross mass, or 400 kilograms. Keep in mind, all of our calculations to this point encompass a 2,000 kilo payload. This is enough to carry one MMSEV vehicle for surface exploration, plus 6 weeks of provisions or additional fuel. The launch sled masses at about 12,500 kilos, including about 2,000 kilograms of SRBs. This is not counted towards the vehicle's total mass, since this mass is discarded within a second of the vehicle leaving the launch track. However, the SRBs remain attached during the first minutes of ascent. Perhaps the most important aspect of this design is its air liquefying engine, working in conjunction with a supersonic combustion engine, or scramjet. Being able to pull rocket oxidizer out of the air is obviously a huge advantage, but in normal situations this demands a lot of energy. At 1 atmosphere, oxygen gas must be cooled below -180 degrees Celsius to become liquid. Perhaps the most important aspect of this design is its air liquefying system, which works in conjunction with a supersonic combustion engine, also known as a scramjet. Being able to pull rocket oxidizer out of the air is obviously a huge advantage, but in normal situations, this demands a lot of energy. At 1 atmosphere pressure, oxygen gas must be cooled below -183 degrees Celsius to become liquid. When the air scoop picking up this oxygen is moving past Mach 5, or hypersonic velocity, the pressure exerted raises this temperature significantly. Circulating a cryogenically cooled rocket fuel around the intake, in this case liquid hydrogen, causes a phase change of atmospheric molecular oxygen in air into liquid oxygen. The scramjet and liquid rockets share their fuel source, liquid hydrogen, delivered by a dual-speed cryogenic pump. The ability to replenish oxidizer in flight also offers an opportunity to supplement the scramjet with oxidizer at high altitude, where air is less dense. In a normal turbine jet engine, using an oxidizer instead of scavenging air can cause severe damage, as turbine components are designed to work within narrow force tolerances. A scramjet, on the other hand, has no delicate moving parts, making this a real option. The intake scoop has a duct where air liquefaction takes place, and excess air is allowed to bleed into the scramjet, preventing the system from producing too much unwanted drag. The need for a microwave ablation system arises from high-tempo orbital operations or thin-margin lunar insertions. It also offers an opportunity to decelerate the spacecraft on return to Earth or landing on Luna or Mars, provided infrastructure exists. This allows an opportunity to use the heat shield mass as a propellant for a lunar landing. The Apollo Lunar Excursion Module expended 1,696 meters per second in its final suicide burn to land on the Moon. Using the ablator, our vehicle could cut this requirement by around 15%. It's possible to imagine a vehicle landing on the Moon, refueling on its surface, then taking off and returning to Earth and re-entering using the microwave ablation system 4 times in total. This makes the prospect much more attractive, especially if a method is devised to replace the ablator during refueling periods. Vehicles such as the Space Shuttle used heavy thermal tiles due to the wing loading of its small wings. Vehicles with larger wing loading of re-entry forces do not need heavy and maintenance expensive thermal tiles. Carbon-based leading edges are sufficient to manage heat. The underside of the vehicle is covered in the ablator material in a thickness of several centimeters or more as required. Ideally, this material would be sprayed on or applied in patches and thermally or chemically bonded, making replacement cost and maintenance far superior to heavier spaceplane concepts. It's also possible to use the ablation system in deep space maneuvers. This would be more practical if a similar system were already in place to handle cargo and raw material transfer between bodies. For example, consider a mining operation on a near-Earth object with low delta-V requirement to reach the Moon, say 160 meters per second. Instead of attaching mined materials to rockets, they are packaged in simple containers with an ablator on both ends. A solar-powered microwave emitter attached to the asteroid accelerates the package into a lunar injection, and arrays in orbit or on the Moon's surface decelerates them into a parking orbit. If this kind of system were already in place, it could be used to assist spaceplanes as well. Microwave arrays on bodies without an atmosphere can use higher, more efficient frequency ranges than the 94 GHz required on Earth, so a lunar installation would draw considerably less power than a terrestrial one for the same delta-V potential. The railgun launch system will require scaled-down testing for proof of concept. Friction will be substantial due to the speed and weight of the vehicle, but this can be mitigated in a variety of ways. One option for reducing friction is to couple the sled to the launch rail using magnets. Maglev trains have demonstrated how heavy vehicles can be levitated on magnetic rails over multi-kilometer distances without excessive cost or complexity. A large amount of electrical power must be transmitted to the armature, so the connection needs to be robust. This is a railgun after all. Smaller scale military railguns transmit current through a plasma arc in the air gap between the armature and the rail, though this hampers efficiency. Mechanical contact generates friction, but also increases conductivity to the armature. Railguns are inherently inefficient, so the choice between loss of efficiency to friction or to plasma is ultimately a choice between two evils. If the contact surface is too small, extreme heating will result on the armature. Too large, and friction will similarly generate excessive heat. In practice, we'll most likely use a combination of mechanical coupling techniques while cryogenically cooling parts of the rail to manage heat. For example, the armature can be given lift properties that allow most of the vehicle's mass to be countered by lift effects, vastly reducing the friction coefficient. The solid rocket booster stage that punches the vehicle up to hypersonic velocity can be configured for a variety of test situations and missions. The example mission uses two custom-made 1,000 kilogram boosters, each delivering 300 meters per second delta V. This implies lengthy and expensive research and development, so there's also an option for a cluster of 10 Star 15 SRBMs from Northrop Grumman, a popular and reliable upper stage kick motor. If we want to conserve vehicle fuel or increase payload mass, we can instead use dual Castor 1 motors, weighing 5,200 kilograms, each supplying a whopping 635 meters per second delta V. These more powerful SRBMs allow the vehicle to retain more of its fuel for deep space maneuvers, though with less overall efficiency. It's also worth mentioning, the launch rail will need to be capable of carrying all additional mass added. The real appeal of this concept comes from its broad mission capability. The configuration we've described is capable of impressive maneuvers. It can go from the surface of Earth to orbit, then transfer to a circular lunar orbit without refueling with a 2,000 kilogram payload. This is enough mass for a MM-7 surface exploration vehicle with a 14-day supply capacity plus an additional month's worth of supplies or smallsats and equipment. Also think about operational tempo. SpaceX has sought the FAA's approval for 25 launches in 2025, and will seek 52 launches per year by 2027. Elon Musk has stated the end goal of multiple Starship launches per day. This comes with caveats. SpaceX would use multiple launch pads, and only the booster stage could achieve a turnaround of a few hours. The upper stages would take 1 to 2 weeks to refurbish between flights, implying SpaceX would have dozens of Starship upper stages on hand. Let's compare. Starship's upper stage weighs in at about 1.2 million kilograms fully fueled. Our spaceplane is about 1.7% the mass of Starship's upper, including fuel. Its payload to mass ratio is about the same, which is notable considering heavier vehicles tend to have better thrust to weight ratio. In order to launch one Starship, the upper stage and lower must be transported to the pad, stacked, and fueled. Multiple launches per day is possible, but clearly ambitious. Compare this to our spaceplane. Vehicles are loaded on their sleds and launched. Multiple sleds can be placed on the launch rail, with the crane loading the first in line for each launch. The sled and vehicle are both recoverable, and because they are so much lighter, transporting them is greatly simplified. If Starship is able to achieve 4 launches per day, once every 3 to 6 hours, our concept should be able to reach a maximum tempo of 1 launch every 5 minutes, or between 1 to 200 launches per day. Overkill for most situations, but still worth noting. These flexible payload capacities, paired with the vehicle's low cost and high operational tempo, offer some unique missions. We can imagine 3 to 4 manned vehicles launched over the course of 2 weeks, which travel to the moon with up to 12 astronauts on board. These arrive at the moon days apart and land in close proximity. One carries an ISRU unit for extracting water from the regolith and cracking it into oxygen and hydrogen gas. The second vehicle carries a 0.5 megawatt microreactor, stripped of its radiation shielding, that will be entombed in regolith to protect humans nearby. Such reactors have limited thermal to electric efficiency, around 25 to 30%, so they also circulate thermal working fluid into the ISRU system to melt ice, to use waste heat more efficiently. The third vehicle might carry a MM-SEV outfitted with a mechanical arm that functions as a crane and as a digging tool. The fourth carries additional fuel in large pressure vessels and supplies. Let's look at this hypothetical on a day-to-day basis timeline. On day 1, the first vehicle carrying fuel and supplies arrives, and its crew get to work preparing the landing site using ground-penetrating radar to find a suitable site to dig in the nuclear reactor. On day 3, as they continue unloading their supplies, the second vehicle lands nearby. A conduit is laid, and the additional fuel tank carried in the first craft's payload is emptied into the second vehicle using an umbilical. The empty tank is then removed from the bay. The third vehicle arrives on day 6, carrying the MM-SEV. An addition welcomed by the astronauts, who have spent the last 3 to 5 days resting in their cramped cockpits and eating and sleeping in their suits. The MM-SEV immediately goes to work excavating a trench for the reactor and setting up the ISRU unit, still unassembled inside the second vehicle's payload bay. On day 9, the fourth vehicle lands, and the MM-SEV unloads its nuclear reactor into the trench. Regolith is pushed over the device, and it's powered on, allowing the ISR unit to begin making water and cracking hydrogen. The additional fuel tank that was emptied on day 3 is attached to the ISRU unit, providing a reservoir of potable water. The second vehicle, its fuel tanks full from the transfer that occurred on the third day, has been using power from the nuclear reactor to reduce fuel boil-off. The first crew, now nearing their third week on the lunar surface, board the vehicle and return to Earth with lunar samples. At the same time, an unmanned vehicle arrives and takes its place, providing additional supplies and another MM-SEV. The 8 astronauts remaining on the lunar surface now all have comfortable accommodations and enough supplies to continue prepping the site for up to a month. New unmanned vehicles arrive every 3 to 4 days, ensuring there is always enough fuel on hand to allow the entire ground team to return to Earth in case of emergency, while bringing in new construction materials. By day 32, the mission's planned timeline has expired. A second nuclear reactor was installed, increasing total power capacity at the site to 1 megawatts. A shelter was constructed using structural parts from one of the vehicles and regolith concrete, then pressurized using gases from the ISRU cracker. A total of 14 landings occurred, 4 manned, 10 unmanned. 4 vehicles have returned to Earth. The mission site is left uninhabited, but not for long. Another crew will arrive in a few weeks to expand the settlement and begin exploring nearby features using the MM-SEVs. Let's pivot to a different situation. The vehicle is launched with a payload of additional fuel and 2 crew during an ideal Mars launch window. A second unmanned vehicle is launched shortly after and synchronizes its orbit with the first. This one's payload bay is loaded with fuel, and the crew capsule has been replaced with consumable supplies. 2 more unmanned launches follow, both carrying fuel. They rendezvous with the first 2 vehicles and refuel them in orbit, then deorbit and land on Earth. The 2 vehicles remaining in orbit perform a 4.8 km per second high-velocity intercept burn for Mars, with a 96 to 100 day ETA. Supplies dwindle by day 30, and the crew transfers supplies from the second vehicle at this time, also regaining about 0.2 km per second delta V from its fuel tanks. The unmanned vehicle will enter Mars' atmosphere at a steep angle and burn up. The manned vehicle, lacking the fuel required for braking maneuver to acquire Mars orbit, will aerobrake instead. Arriving at interplanetary speed, the vehicle performs a brief burn to shed some velocity, and then begins to aerobrake, encountering the thin upper atmosphere at hypersonic speed. The scramjet kicks in immediately, allowing the vehicle to control its rate of descent to slow down as much as possible without burning up. The remaining ablator on the vehicle's belly burns, and further assists the deceleration. Studies have shown the Mars aerobrake option is highly attractive, since it requires less fuel and allows faster transfers. Once the vehicle has slowed sufficiently, it engages its scramjet and maneuvers to the designated landing site. The The ability to fly in the Martian atmosphere allows the vehicle to reach places that would be difficult to reach from an equatorial orbit, such as the poles. Polar ice or glacial floodplains may provide an ideal landing environment for spaceplane. Landing is accomplished with a set of skids and a drogue chute. The mission is declared a success. Within a week, unmanned vehicles will begin to arrive, carrying supplies and a ISRU unit capable of producing hydrogen gas from polar ice. This gas is liquefied under pressure and pumped into the tanks as fuel. Once fully replenished, the vehicle has again reached its capacity of about 5.1 kilometers per second delta V. It uses its liquid engines for takeoff, then activates the scramjet to ascend to near orbital velocity. It expends about 4 kilometers per second delta V to acquire a low Martian orbit, leaving it with just over 1 kilometers per second delta V in the tanks. The vehicle now has several options. It can refuel in Mars orbit using pre-established assets, or it can visit Phobos and Deimos without further refueling. When it's time to return to Earth, two things will be required: a full tank of fuel and another unmanned vehicle in Mars orbit with a full tank and its crew capsule mast replaced with supplies, just like the first vehicle that left with the manned vehicle on the Earth to Mars leg. Another 3 to 4 months will elapse as the pair of craft traverse deep space on an aerobrake intercept with Earth, finishing the return mission with a scramjet-powered descent and runway landing. The vehicle we've discussed today is intended for high-tempo use and wide mission capability, while also being inexpensive enough to replace or refit rather than rapidly reuse. The goal is between 50 and 100 launches per year, using one launch complex, with an average of 1 to 2 launches per week. Though as we've said, this rate could easily be increased to 100 launches per day or more. The extremely low cost of these vehicles makes their payload cost per kilogram much lower than current space access leaders like SpaceX. But this advantage has a hidden cost. To employ these vehicles, substantial launch infrastructure investment is needed. All components, systems, and technologies must be proven before they can be flown when manned missions are the goal. The least tested aspects of this concept are the launch rail system and the air liquefaction system, in conjunction with the scramjet. Scramjets are proven technology, but few planned vehicles have attempted to liquefy air in flight to feed them. The most prominent vehicles to use a system like this was the British HOTOL spaceplane concept. This never flew, and the NASA X-43 testbed has also planned to test such a system. The microwave ablation system is similarly untested. Technically, it can be omitted at the cost of some 100 to 300 meters per second delta V, and test flights may be conducted without the microwave assist. This system is really intended to lower vehicle cost while increasing delta V available for deep space maneuvers. The railgun system does have precedent. NASA has experimented with high-velocity rocket sleds, and the US Navy has tested large-scale railguns, though nowhere near the scales discussed here. We'll need a dramatically new approach to railgun design to achieve the 1400 meters per second exit speed hypothesized. Of course, we can always opt for a shorter rail and lower exit speed, and increase the solid rocket mass to compensate. Because the solid rockets and sled represent considerably less mass than the vehicle itself, we have ample room to scale up the sled. Alternatively, we can reduce the vehicle's 2,000 kilogram payload. All of the challenges inherited by this design can be mitigated in scaled-down testing environments. Further, although manned flight is a major focus of our analysis, there is significant benefit to using unmanned vehicles. When G-forces are not a concern, the launch track can be reduced to 1.5 kilometers or less, and the payload can be increased up to 3,600 kilograms or more. Given the significant advances in computerized vehicle control, it would be short-sighted to rely solely on manned launches. We can imagine a situation where a 1.5 kilometer launch trail is constructed, and over the course of the following years, microwave arrays are constructed as budgets allow. Unmanned launches occur frequently as the rail is gradually lengthened. Within a matter of years, the infrastructure is fully realized within the limits of a nominal NASA budget item. We should mention that all launch infrastructure here is energy demanding. The railgun will be expected to operate at 50 to 80% efficiency. The microwave ablation system will work at much lower efficiencies, of between 10 and 30%. To propel the vehicle and sled, about 32,500 kilograms combined, to 1,400 meters per second, the railgun will impart 31.9 gigajoules of energy. Assuming a nominal efficiency, this will demand about 4,670 megawatts. The beamed energy system will act on the vehicle for about 100 seconds, inducing about 3.95 gigajoules of force on the vehicle from ablation. This will require about 40 megawatts delivered to the ablator, with an efficiency of 20%. This means the array must produce at least 260 megawatts. The microwaves we're using here operate at a lower frequency than the optimal 94 GHz, meaning our actual energy demand will be higher than the value we just calculated. But it's unlikely demand of the microwave system will exceed 1 gigawatts continuously. Assuming both systems draw from the same power grid, at a glance the peak energy use will reach 4.6 gigawatts for about 12 seconds. This figure can be managed further. For example, extending the launch rail will lower energy use considerably. Increasing acceleration time from 11.9 to 14 seconds reduces power demand by around 25%. Because energy demand only surges for 12 seconds, it's not necessary to provide this power using energy infrastructure directly. We can store energy in flywheels or capacitors, so the daunting prospect of using 4 to 5 independent nuclear reactors continuously is not a real concern. A single 1 gigawatt nuclear reactor, such as the Westinghouse AP1000, can deliver all energy needs. The AP1000 is an ideal candidate for this role since it has a proven track record around the world and can be integrated with other support infrastructure, since its pressurized water design does not require the large concrete enclosures common to other reactors. Even though we chose railguns for our discussion here, other systems like the kinetic slingatron or explosive blast wave accelerator could also be used. If we're restricted to unmanned payloads, an explosive launch could be accomplished with a far shorter launch tube at extremely low cost. We have a SSTO concept here that is viable with modern technology, easy to test and scale, and affordable compared to the alternatives. It can also exceed the capabilities of some of its full-stack competitors such as SpaceX's Starship and capsules like Orion or Dragon. The project also promises potential investment opportunities for a wide range of industries, including nuclear, defense, beamed energy, and aviation. We can learn from similar ventures, such as Reaction Engine's HOTOL, what kind of challenges projects like this face and how to overcome them. HOTOL captured the imagination of the British public, spreading into the US defense contracting space shortly after. In the 1980s, at a time when there was a real desire to develop spaceplanes, a true SSTO like HOTOL bore obvious advantages versus designs like the Space Shuttle. We should note just how successful HOTOL's initial reception was, even though it eventually failed. The concept for an unmanned hypersonic SSTO spaceplane was picked up by the British Ministry of Defense, and collaborated on by Rolls-Royce. Reaction Engines developed the design from around 1984 to the mid-1990s, iterating on their design into the modern Skylon. Work on Skylon continued into 2024 when it was cancelled, marking 40 years of development. The game was being played right to the very end, but to cross the Valley of Death in aerospace is very hard. The Valley of Death refers to the span of time between concepting and realizing a design in the aerospace industry. This can take 20 years or longer, and many projects have met their demise awaiting government action or investment opportunities. Interest in hypersonic spaceplanes has never been greater. However, the failure of popular designs like HOTOL and later Skylon have left a bad taste in the mouth of the investing public. European companies with smaller budgets and fewer reliable vehicle options than NASA are still actively pursuing the spaceplane route, with new designs like Invictus promised for flight testing by 2031. Hypersonic planes without a clear orbital capability have continually seen success in the private sector, Notably, Virgin Galactic's ventures have always set their sights on a suborbital passenger plane, even before they set their sights on orbital space-capable vehicles. Sierra Space has developed Dream Chaser, and Hermes Corporation plans on bringing a Mach 5.5 suborbital jet to the market. In 2021, Boom Hypersonic partnered with United Airlines, who pre-purchased 15 30-seat vehicles for commercial use. Russia and China have similar efforts underway, split between private and government efforts. These developments are promising, but how soon we'll see hypersonic commercial air travel enter the picture has yet to be determined. When the time does come, we will be primed for similar vehicles with orbital capabilities and beyond.